It is normal and acceptable for a small amount of neutral current to flow on the meter can and intermediate metal conduit (IMC) pipe in a typical residential service where the overhead neutral is bonded to the meter can. This occurs because the neutral conductor isn't isolated from the grounded parts of the electrical system, which includes the meter can and the IMC pipe. Consequently, a small portion of the current will naturally flow through these grounded components due to any imbalances in the electrical loads placed in the service. The magnitude of neutral current flowing through the grounded parts depends directly on the extent and nature of unbalanced loads, specifically their magnitudes and phase angles. Larger imbalances in the loads typically result in a greater flow of neutral current. However, the neutral current should remain relatively small and should never exceed the current carrying capacity or ampacity of the grounded parts of the system. The National Electrical Code, or NEC, mandates that all grounded parts of an electrical system be bonded together. This is to ensure that they all maintain the same electrical potential. This bonding is a critical safety measure, helping to prevent electrical shock hazards and ensuring the overall safe operation of the electrical system. Furthermore, the NEC also requires that the neutral conductor be bonded to the grounded parts of the system, specifically at the service entrance. This particular bonding creates a low impedance pathway for the neutral current to flow, which effectively prevents the neutral conductor from becoming energized unexpectedly. In a residential service scenario where an overhead neutral is bonded to the meter can, the IMC pipe is also bonded to the meter can through the 3-wire cable that supplies power to the main disconnect. This bonding arrangement ensures that the IMC pipe maintains the same electrical potential as both the meter can and the neutral conductor. Therefore, the small amount of neutral current flowing through the IMC pipe is considered normal and acceptable within the established safety and operational standards. To further clarify, let's delve into the reasons behind these requirements and the implications of neutral current flow. The neutral conductor in an electrical system is intended to carry the imbalance of current between the hot or phase conductors. In a perfectly balanced three-phase system, the neutral current would ideally be zero. However, in most real-world scenarios, especially in residential settings, loads are not perfectly balanced. This imbalance results in current flowing through the neutral conductor back to the source, typically a transformer supplied by the utility. When the neutral is bonded to the meter can and the grounding system, a parallel path is created for the neutral current. This means that a portion of the neutral current will flow through the grounding system, including the meter can and the IMC pipe, back to the source. The amount of current that flows through the grounding system depends on the impedance of the various paths. Impedance is the total opposition to current flow in an alternating current, or AC, circuit, and it includes both resistance and reactance. The path with the lowest impedance will carry the largest portion of the current. The NEC addresses this by requiring that the grounding system be designed to have a lower impedance path to ground. This is achieved through proper bonding and the use of appropriately sized grounding conductors. The purpose of this low impedance path is to ensure that fault current can quickly flow back to the source, trip a circuit breaker or fuse and clearing the fault. This rapid clearing of faults is essential for preventing electrical shock hazards and minimizing damage to equipment. The bonding of the meter can and IMC pipe is typically achieved through the use of bonding bushings and bonding jumpers. A bonding bushing is a type of fitting that is installed on the end of a conduit and provides a connection point for a bonding jumper. A bonding jumper is a short length of conductor that is used to connect two metallic parts of the electrical system together. In the case of the meter can and IMC pipe, a bonding jumper would typically be installed between the bonding bushing on the IMC pipe and the grounding lug on the meter can. This bonding jumper ensures that the IMC pipe is electrically connected to the meter can and the grounding system. The size of the bonding jumper is determined by the size of the service entrance conductors, as specified in the NEC. The NEC provides tables that specify the minimum size of grounding and bonding conductors based on the size of the service entrance conductors. These tables are designed to ensure that the grounding and bonding conductors are adequately sized to carry fault current. In addition to bonding the meter can and IMC pipe, it is also important to ensure that all other metallic parts of the electrical system are properly bonded. This includes things like metal enclosures, equipment grounding conductors, and metallic water pipes. All of these metallic parts should be bonded together to create a continuous grounding system. The continuous grounding system provides a low impedance path for fault current and helps to prevent electrical shock hazards. It is important to note that the flow of neutral current in the grounding system is not without its potential drawbacks. One potential issue is the creation of ground loops. A ground loop occurs when there are multiple paths for ground current to flow, creating a loop. This loop can act like an antenna, picking up electromagnetic interference, or ME, and introducing noise into the electrical system. Ground loops can be particularly problematic in sensitive electronic equipment, such as audio and video systems. To minimize the risk of ground loops, it is important to follow good grounding practices and to avoid creating multiple ground paths. This can be achieved by using a single point ground and by avoiding the use of multiple grounding electrodes. Another potential issue is the possibility of corrosion. When current flows through a metallic conductor, it can cause corrosion, especially in the presence of moisture and dissimilar metals. This corrosion can weaken the conductor and eventually lead to failure. To minimize the risk of corrosion, it is important to use corrosion-resistant materials and to protect the grounding system from moisture. In summary, the flow of a small amount of neutral current on the meter can and IMC pipe in a residential service is normal and acceptable. This is due to the neutral being bonded and unbalanced loads. The NEC requires bonding for safety and a low impedance path for fault current. However, it is important to follow good grounding practices to minimize the risk of ground loops and corrosion. The specific requirements for grounding and bonding are outlined in Article 250 of the NEC. This article provides detailed information on the proper methods for grounding and bonding electrical systems. It covers topics such as grounding electrode systems, equipment grounding conductors, and bonding jumpers. It is important to consult Article 250 of the NEC when designing or installing an electrical system to ensure that it is properly grounded and bonded. Firstly, grounding electrode systems establish a connection to the earth, providing a reference point for the electrical system's voltage and a path for fault current to flow back to the source. Common grounding electrodes include metal underground water pipes, ground rods, and ground rings. Secondly, equipment grounding conductors provide a low impedance path for fault current to flow from electrical equipment back to the source. These conductors are typically copper or aluminum and are run along with the circuit conductors. Thirdly, bonding jumpers are used to connect metallic parts of the electrical system together, ensuring that they are all at the same electrical potential. This helps to prevent voltage differences that could create a shock hazard. The size of grounding and bonding conductors is determined by the size of the service entrance conductors, as specified in the NEC Table 250.102 colon. This table provides minimum sizes for grounding and bonding conductors based on the size of the ungrounded conductors. It is important to use the correct size conductors to ensure that they are capable of carrying fault current. The NEC also addresses the bonding of specific equipment, such as meter cans and metal conduits. Section 250.92 specifies the requirements for bonding metal enclosures and raceways. It requires that metal enclosures and raceways be bonded to the grounding electrode system to provide a low impedance path for fault current. In the case of a meter can, the neutral conductor is typically bonded to the meter can enclosure. This bonding provides a path for neutral current to flow back to the source, as well as a path for fault current. The IMC pipe is bonded to the meter can through the use of bonding bushings and bonding jumpers. The bonding bushing provides a connection point for the bonding jumper, which is then connected to the meter can enclosure. This ensures that the IMC pipe is electrically connected to the meter can and the grounding system. The NEC also addresses the issue of ground loops. Section 250.6 prohibits the creation of ground loops that could introduce noise into the electrical system. It requires that grounding systems be designed to minimize the flow of circulating current. This can be achieved by using a single point ground and by avoiding the use of multiple grounding electrodes. In addition to the NEC requirements, There are also industry standards and best practices that should be followed when grounding and bonding electrical systems. These standards and best practices can provide additional guidance and ensure that the electrical system is properly grounded and bonded. For example, the Institute of Electrical and Electronics Engineers, or IEE, has developed standards for grounding and bonding in industrial and commercial power systems. These standards provide detailed information on the design and installation of grounding systems. Another important consideration is the type of soil in the area. The soil resistivity can affect the performance of the grounding electrode system. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to improve the soil conductivity. The NEC provides guidance on how to improve soil conductivity, such as by using ground-enhancing materials. Finally, it is important to regularly inspect and test the grounding system to ensure that it is functioning properly. This includes checking the connections for corrosion and measuring the impedance of the grounding system. Regular inspection and testing can help to identify potential problems before they become safety hazards. In conclusion, the flow of a small amount of neutral current in the meter can and IMC pipe is normal and acceptable in a residential service. This is due to the neutral being bonded and unbalanced loads. However, it is important to follow the NEC requirements and industry best practices for grounding and bonding to ensure the safety and reliability of the electrical system. This includes properly bonding all metallic parts of the system, using appropriately sized grounding and bonding conductors, and minimizing the risk of ground loops and corrosion. By following these guidelines, it is possible to create a safe and effective grounding system that protects against electrical shock hazards and ensures the proper operation of electrical equipment. Always consult with a qualified electrician when working on electrical systems to ensure that the work is performed safely and in accordance with all applicable codes and regulations.